In this video, we're going to talk about suggested homework problems from section 8.3, trigonometric integrals. Let's go ahead and get started with number one. Which of the integrals requires more steps to find and explain but do not integrate? So the first integral of sine to the 8th x dx takes more steps. It would require several trig identities to rewrite it, whereas the integral of sine to the 8th x cosine of x dx is a basic u substitution. This is simple, so we would let u equal to sine x, du equal to cosine of x dx, and this would be in the form of u to the 8th du. Very simple. We're not supposed to solve it, so we'll move on to number three. As we go forward, let's just remember that we're looking for some patterns here of things that are in the form of sine to the n, u, cosine u du, or cosine to the n, u, sine u du, and I can make this negative here because the derivative of cosine is negative sine. Things in the form of tangent to the n u secant squared u du. This will be equal to sine to the n plus 1 over n plus 1 plus c. This is cosine to the n plus 1 over n plus 1 plus c. This is tangent to the n plus 1 over n plus 1 plus c. Cotangent to the n, this is negative u, cosecant squared u du, and we can fix this with a negative, and then that's going to be negative cotangent to the n plus 1 over n plus 1 plus c. We have secant to the n of u, secant u, tangent u du, and that will be secant to the n plus 1 over n plus 1 plus c of u, and u here. Cosecant to the n u, cosecant u, cotangent u du. Negative is cosecant n plus 1 u over n plus 1 plus c. Those are our basic forms that we're going for in this section. We also have things like the integral of secant u du. Remember that to be ln of secant u plus tangent u plus c. The integral of cosecant u du is equal to negative ln of cosecant u plus cotangent u plus c, or that's also ln of cosecant u minus cotangent u plus c. You have, just as a reminder, that integral of tangent u du is equal to ln of secant u plus c, or a negative ln of cosine u plus c and an integral of cotangent of u du is equal to negative ln of cosecant u plus c, or ln of absolute value sine u plus c. All of these ln rules have absolute values unless you are certain in some way from the domain of the problem that they're forced to be positive. All right, moving forward, now that we've had that little review, you've also got all of your basic ones that can show up, but I'm not going to refresh all of those. Cosine to the fifth of x sine x dx, that u is cosine of x, du is negative sine x dx. So negative will be u to the fifth. Du is negative 1/6. U to the sixth plus c is negative 1/6 cosine to the sixth u. I'm sorry, to the sixth x plus c. Let's look at 7. Integral sine cubed cosine squared x dx. So I have an odd power of sine. I'm going to hold one over here to become du. That means that I'm going to change my sine squareds that remain into a 1 minus cosine squared with the Pythagorean identity. And this makes cosine squared x sine x dx minus integral cosine to the fourth x sine x dx. I need a negative sine x dx for my du and a negative sine x dx for my du there. So this is u to the second du plus u to the fourth du is a negative 1/3 u to the third plus 1/5 u to the fifth plus c. U is equal to cosine of x, and du is a negative sine x dx. So this is a negative 1/3 cosine to the third x plus 1/5 cosine to the fifth x plus c. Let's look at the next problem. Integral 8x cosine squared x dx. Recall your power reducing formula that says cosine squared x is equal to 1 plus cosine of 2x over 2. So I'm going to rewrite this to get rid of that even power of cosine. 8x times 1 plus cosine 2x over 2 dx, and this 2 goes into this 8 4 times, and then I have integral 4x times 1 plus cosine 2x dx is integral 4x dx plus integral 4x cosine of 2x dx. I'll split these up here, and this will be 4 integral x dx plus 2 integral x cosine 2x 2 dx. I'll take 2 from that 4 to make a cosine u du. So this one is going to be by parts. This one is just 2x squared plus 2 times my u is x, and my dv is cosine of 2x 2 dx. So v is going to be sine 2x. du will be dx. So uv is x sine 2x minus the integral of v du sine 2x 2x dx. So that's going to be 2x squared plus 2x sine 2x minus 2 integral sine 2x dx. So I'm just going to move this 2 inside because I need it to complete my du in there. So this is going to be 2x squared plus 2x sine 2x minus integral sine 2x 2 dx. So this is a sine u du, and the integral of sine u is a negative cosine u. So this is 2x squared plus 2x sine 2x plus cosine of 2x plus c. And we'll just leave it like that. No need to try and get rid of those double angles. Let's move on to number 21. Integral of secant 4x dx, put a 4 and a 1/4 to make this 1/4. Integral secant u du, which is 1/4 ln of secant u plus tangent u plus c. It's 1/4 ln of secant 4x plus tangent 4x plus c. Moving on now to number 27. Integral tangent cubed 2t, secant cubed 2t dt. So I'm going to hold a secant tangent and change everything into secants. So this is secant 2t tangent 2t, and I like those other two secants that are there, and I want to change these two tangents here. Tangent squared theta plus 1 is equal to secant squared theta. So tangent squared theta is secant squared theta minus 1. So secant squared 2t minus 1 integral secant to the 4th 2t minus secant squared 2t secant 2t tangent 2t 2 dt, and a 1/2 out front here. So that will be 1/2 of secant to the 5th 2t over 5 minus 1/2 of secant to the 3rd 2t over 3 plus c is 1/10 secant to the 5th 2t minus 1/6 secant to the 3rd 2t plus c, where my u was secant 2t and my du was secant 2t tangent 2t dt. All right, let's look at number 29. Says integral secant 6 4x tan 4x dx. I'm going to hold a secant tangent off to the side again. At 4 and 1/4, and the remaining pieces here will be secant to the 5th 4x. So that's 1/4 of secant to the 6th 4x over 6 plus c. It's 1/24 secant to the 6th 4x plus c. Looking at number 33. 33 says integral of tangent squared x over secant x dx. So because I have a monomial in the denominator of secant, if I can change my numerator into the Pythagorean identity that includes secant squared, I can simplify. So tangent squared plus 1 is equal to secant squared. So tangent squared is equal to secant squared minus 1. So integral secant squared minus 1 over secant is going to be an integral of secant minus a 1 over secant, which is a cosine. And so this is ln of secant x plus tangent x. That's in absolute value bars inside the ln minus sine x plus c. Let's move on to number 37. Says y prime is equal to tan cubed 3x secant 3x. So y of x is equal to antiderivative of tan cubed 3x secant 3x dx. And so probably want to hold a secant tangent again and change the tangents to secants. So let's make this a secant 3x tangent 3x 3 dx and put a 1/3 out here. And then that tangent squared that's left, we're going to change into secant squared 3x minus 1. And so y of x is equal to 1/3 of integral secant squared 3x times secant 3x tangent 3x times 3 dx minus integral minus 1/3 integral of secant 3x tangent 3x 3 dx. So y of x is equal to 1/3 of secant to the third 3x over 3 minus 1/3 of, and then that's just the derivative of regular secant 3x plus c. So a third times another third is 1/9 secant cubed 3x minus 1/3 secant 3x plus c. All right, let's look at 49. There it is. Cotangent cubed 2x dx. And we're going to save a cotangent. And we're going to have a cotangent squared. And 1 plus cotangent squared is equal to cosecant squared. So I'm going to go cotangent 2x times cosecant squared 2x minus 1 dx. And we'll put the 2 here and the 1/2 because I know I'm going to need it. 1/2 integral cotangent 2x cosecant squared 2x dx minus integral cotangent 2x 2 dx with the 1/2 up front here. Now I actually need the derivative of cotangent as a negative cosecant squared, so negative and negative here. And that's going to give me negative 1/2 cotangent squared 2x over 2 minus 1/2. And then the integral of cotangent u du is going to be a negative ln of cotangent u plus cosecant u, or cosecant plus cotangent. I'll say cosecant plus cotangent plus c. No, not cosecant, cotangent, cosecant. There we go, like that. And then shoot, if that were cosecant, it would be cosecant cotangent. All right, that's sufficient, I think, for the solution. The book goes further in trying to get this back into a different form that really doesn't seem necessary to me, so I'm going to leave it there and leave it for you to get it into the form of the answer in the back of the book if you would like to try that yourself. So let's look at number 59. And negative pi to pi sine squared x dx. So we're going to use our power reducing formula here. Negative pi to pi, 1 minus cosine 2x over 2 dx is 1/2 of negative pi to pi, 1 minus cosine 2x dx. It's 1/2 negative pi to pi of dx minus 1/2 negative pi to pi of cosine of 2x dx. And we'll put 2 here and 1/2 here to fix it. And this is going to be 1/2 of x from negative pi to pi, negative 1/4 of sine of 2x from negative pi to pi. So this is 1/2 of pi plus pi, because minus a negative pi is plus pi, minus 1/4 of sine of 2 pi is 0, minus sine of negative 2 pi is also 0. So this is 0. This is 1/2 of 2 pi is pi. Let's look at number 65. Integral negative pi over 2 to pi over 2, 3 cosine cubed x dx. So save a cosine, change the cosine squared, pull the 3 out, negative pi over 2, pi over 2, save the cosine, x, change the cosine squared to a 1 minus sine squared x of 3, integral negative pi over 2 to pi over 2 of cosine of x dx minus 3 integral sine squared x cosine x dx, negative pi over 2 to pi over 2. Integral of cosine is sine, so this is 3 sine x, with sine x being evaluated from negative pi over 2 to pi over 2 minus 3, and then this needs to be derivative of sine is cosine, so that's good. Sine cubed x over 3, and then no plus c, because this is going to be evaluated from negative pi over 2 to pi over 2. So we have 3 times sine of pi over 2 minus sine of negative pi over 2 minus sine of pi over 2 cubed minus sine of negative pi over 2 cubed is 3. Sine of pi over 2 is 1 minus sine of negative pi over 2 is negative 1 minus sine of pi over 2 is 1 minus sine of negative pi over 2 is negative 1. So this is 3 times 2 minus 1d1 plus 1 is going to be 6 minus 2 is 4. Let's look at 71. Has y is equal to sine x and y is equal to sine cubed x. And remember that sine has to stay between negative 1 and 1 because we're above the x-axis here. We're staying between 0 and 1, so that's a fractional amount. And if I cube a fraction, I get a smaller fraction than the fraction itself. So sine cubed is going to be smaller, so the order of subtraction here to get the area is sine of x minus sine cubed of x. And we're just getting the area from 0 to pi over 2 dx. So this is going to be 0 pi over 2 sine x dx. That one's pretty basic. Integral 0 pi over 2 sine cubed. So I'm going to have to hold a sine x and change this to be a 1 minus cosine squared x. And this will be 0 to pi over 2 sine x dx minus 0 to pi over 2 sine x dx plus integral cosine squared x sine x dx 0 to pi over 2. This and this are exact opposites. I don't even need to figure them out. They're going to zero each other out. So I'm going to end up with a negative integral 0 to pi over 2 of cosine squared x times negative sine x dx. That's a u du substitution of u to the n du, where u is equal to cosine of x, and du is equal to a negative sine x dx. I won't actually change everything to u's here. I'll just say that this is negative cosine cubed x over 3, evaluated from 0 to pi over 2. So this is going to be negative 1/3 of cosine of pi over 2 cubed minus cosine of 0 cubed. And that's going to be cosine of pi over 2 is 0 minus cosine of 0 is 1. So that is negative 1/3 times a negative 1 is a positive 1/3. Let's look at 77 now. And we're just supposed to do part A here, where we find the volume of the solid generated by revolving the region about the x-axis. So 77 says y is equal to sine x, y equals 0, x equals 0, x is equal to pi. So let's just draw a quick sketch here. Sine from 0 to pi here. That's what we're talking about. And we'd like to revolve around the x-axis. So rectangles perpendicular to the axis of rotation would be great using the disk washer method, 0 to pi. This will be sine squared x dx because r is sine of x and I need to square my r function. Here I have to use my power reducing formula, pi 0 to pi of 1 minus cosine 2x over 2 dx. I'll make this pi over 2 out here, 0 to pi, 1 minus cosine of 2x dx is pi over 2, 0 to pi, dx minus pi over 2, 0 to pi, cosine 2x dx, and then 2 and 1/2 here is pi over 2, x 0 to pi, minus pi over 4, sine 2x from 0 to pi, pi over 2, pi minus pi over 4, sine of 2 pi is 0, sine of 0 is 0, so this is 0. So this is pi squared over 2 for my final answer. And these are square units since we're talking about area. No, cubic units since we're talking about volume. There we go. All right, that's it for this video. We'll come back next time and talk about suggested homework problems from 8.4, which will be called trigonometric substitution. And it'll be ways to deal with things that involve square roots of a squared minus u squared minus a squared, or a squared plus u squared, or u squared plus a squared, using the idea of the Pythagorean theorem and right triangles, and using those relationships of the right triangle to change messy algebraic expressions into hopefully cleaner trigonometric expressions in terms of the angle theta, and then being able to solve that trigonometric interval using the rules that we learned in this section, and then back substituting back into the algebraic form was something that we couldn't integrate easily in the algebraic form, change it into a trig integral instead, and then change it back. So that's called trigonometric substitution. We'll talk about that next time. See you for the next video.